Welcome you all dear students. In this module, I Dr. Shushma will be talking with you about computation of protein requirements for various age groups. In this section, you will be learning how the protein requirements of various age groups are derived. In the past, a factorial method was used as a basis for predicting the protein requirements of various age groups. For adults, the requirements for dietary proteins was considered to be the amount needed to replace the obligatory nitrogen loss after adjustment for inefficiency in utilization of dietary protein and for the quality of the dietary protein consumed. For children and pregnant and lactating women, an additional amount of protein for tissues growth or milk formation was incorporated into this factorial estimate of requirements. Because of these assumptions required, the validity of the factorial approaches has been questioned. So by this episodes, students will be learning about the general principles, techniques in the derivation of protein requirements for various age groups. Firstly, general principles for estimating protein requirements. WHO in 1985 reviewed the evidence on protein requirements and concluded that adult protein allowances should be based on nitrogen balance studies. For older infants and children, data are sparse. Thus, all lines of evidences are used by the subcommittee in estimating requirements, nitrogen balance, and observed and theoretical needs for adequate growth. For pregnancy, nitrogen balance data were considered, but allowances continue to rely on theoretical depositions of proteins in the fetus and adnexa. New information on human milk volume was used to estimate lactational requirement. Now let us learn about nitrogen balance. Nitrogen balance is the difference between nitrogen intake and the amount excreted in urine, feces and sweat, together with minor losses occurring by other routes. To estimate the protein requirements, levels of dietary protein below and near predicted adequate intake are fed and nitrogen balance is measured at each level. The requirement is estimated by interpolating or extrapolating the nitrogen balance data to the zero balance point for adults or to a defined level of positive balance for children. Let's now learn about estimates of amino acids requirements. In determining the requirements for protein, the subcommittee first considered requirements for the essential amino acids. The required amounts of the 9 essential amino acids must be provided in the diet, but because cysteine can replace approximately 30% of the requirement for methionine and tyrosine about 50% of the requirement for phenylalanine, these amino acids must also be considered. The essential amino acid requirements for infants, children, men and women were studied extensively from 1952 to 1970. Except for infants, where the criterion was growth and nitrogen accretions, the requirement was accepted to be the amount of intake needed to achieve nitrogen equilibrium in short-term studies of adults or positive balance in children. In a novel approach to examine these requirements, the need for 4 amino acids was examined in children whose diets were strictly controlled because of inborn errors of metabolism and who were developing normal. Requirements determined in this way during the first 3 years of life are in good agreement with the values for isoleucine, leucine and phenylalanine plus tyrosine and valine for infants and 2 years of children old. Recommended allowances for proteins. In establishing an RDA for proteins, 3 steps were followed. Firstly, estimating the average requirement for reference proteins according to the sex, age and reproductive status of a woman. Secondly, the standard deviations of requirement was determined and average requirement values were increased accordingly to compute the recommended allowances of reference protein. Thirdly, amino acid scoring patterns were tabulated. These are based on requirements of various age groups for essential amino acids and for total protein. These patterns of requirement were reviewed in relation to US food consumption pattern to determine if adjustments of the allowances for reference proteins would be warranted in establishing the RDA for protein due to amino acids compositions or protein digestibility of food proteins consumed. Now let us learn about the requirement for reference protein and its variability. To determine the protein requirements of younger male adults, WHO in 1985 reviewed evidences from both short and long-term nitrogen balance studies. On the basis of recalculated data from the short studies, the international group proposed a several mean requirement of 0.6 per gram per kg per day for reference protein. Several relatively long-term studies involving single levels of protein intake yielded similar estimates of requirements for subjects consuming egg protein diet. By averaging the two sets of balanced data, a protein requirement of 0.6 gram per kg per day was obtained. This is accepted to be the average daily requirement of reference proteins. No data were available on the coefficient of variance for long-term studies, but for short-term studies, the mean coefficient of variances was established to be 12.5%. A value of 25% above the average requirement would be expected to meet the needs of 97.5% of a normally distributed population. Thus, 0.721 gram per kg per day is the recommended allowances of reference protein for young male adults. Among the elder, the protein content of the adult body diminishes with age. More specifically, non-muscle mass is little affected by age, whereas muscle diminishes extensively and is compensated for by an increase in body fat. These changes in muscle mass are related to the whole body protein turnover and changes in the rate of protein synthesis. Muscle protein turnover accounts for 30% of the total protein turnover in the young adult, but only 20% of that in the elderly. Serum albumin levels and daily albumin synthesis also decreases in the elderly people who consume diets with adequate protein. Recommended allowances for reference protein is accepted to be the same for the elderly as for the young adults because of the difference in the body composition. This allowances is higher per unit of lean body mass and should allow for some decrement in the utilization efficiency. In the pregnancy, additional protein is required during the period for the mother and the fetus. Maternal protein synthesis increases in order to support expansion for the blood volume, uterus and breasts, and fetal placental proteins are synthesized from amino acids supplied by the mother. The magnitude of the required is increased in dietary intake remains uncertain, since different methods of estimations yield different figures. The factorial method of estimating requirements for pregnancy is based on the amount of protein present in the fetus, placenta and maternal tissues, including blood. It's calculated that 90 to 5 grams of proteins is deposited during the pregnancy, involving 12.5 kgs of maternal weight gain and an infant weighing 3.3 kgs at the term. The rate of nitrogen retention is not constant for the first through third trimester. Nitrogen deposition is estimated to be 0.11, 0.52 and 0.92 grams per day respectively. Protein turnover is increased by the 12th week of pregnancy. It remains high in the second trimesters and the same or lower in the third semester. Consequently, increased protein needs during pregnancy may be more uniform across time than the figures of Hyten and Litch indicates. Nitrogen balance data can also be used to estimate protein requirements during pregnancy. Almost all older balance studies have indicated that more nitrogen is retained during pregnancy than is predicted on the basis of fetal and placental growth and maternal tissue heterotropy. In more recent studies, nitrogen retentions have been found to be closer to the theoretical value of allowances and is made for unmeasured losses. Nevertheless, data on changes in body weight and body potassium indicates the nitrogen retentions under laboratory conditions is somewhat greater than can be accounted for only by the fetus and the maternal supportive tissues. This suggests that the protein might be retained at sites other than those now recognized, for example in skeletal muscle. Dietary surveys in developing countries indicate that pregnant women eating self-selected diets generally consume somewhat larger amounts of proteins than theoretical requirements. Moreover, satisfactory levels of protein intake tend to be associated with improved reproductive outcomes. However, such epidemiological data are confounded by the strong dietary correlations between protein and energy as well as their metabolic interrelationships. Despite these discrepancies between factorial and nitrogen balance estimates of nitrogen gain during pregnancy, the subcommittee concurs with WHO 1985 that the estimate of requirements should be based on the factorial method. The coefficient of variance in birth weight is 15%, a variance assigned to all components of pregnancy protein gain. The average storage value is thus increased by 30% to include the protein gains of virtually all healthy women during the pregnancy. These values must be adjusted for the efficiencies with which dietary protein is converted to fetal, placental and maternal tissues. This observed in infant. The additional allowances of reference protein needed to support the deposition of new tissues is calculated to be 1.3, 6.1 and 10.7 grams per day during the first, second and third trimesters of pregnancy, respectively. There is also a maintenance requirement associated with an add-on lean tissue. To allow for this and because of the uncertainty about the rate of tissue depositions, the subcommittee recommends an additional allowances of 10 grams of reference protein per day throughout the pregnancy. The average protein content of mature human milk is approximately 1.1 grams per 100 ml, except during the first month when it's about 1.3 grams per 100 ml by WHO 1885 in lactating period. Analysis of human milk consumptions in the United States based on a study of 40 mothers in the first 4 months of lactation shows a fall in protein content from 1.36 grams per 100 ml to 1.12 grams per 100 ml during this period. The average protein requirements for lactation is estimated from milk consumptions and the mean value of milk produced, which is 750 ml per day, is adjusted for 70% efficiencies in the conversion of dietary protein to milk protein. The coefficient of variations is taken to be 12.5% by WHO 1985% statistics. Thus, the average requirement is increased by 25% to determine the recommended allowances of a reference protein. The volume of milk produced in the second 6 months of lactation is about 20% less than in the first 6 months. According to international data, WHO 1985, the additional allowances in this period is 11.8 gram of reference protein per day. The recommended allowances of additional reference protein is 15 gram per day during the first 6 months of lactating and 12 grams per day thereafter period. Infants, children and adolescents period. During this, the first year of life, the protein content of the body increases from 11 to 15% and body weight increases by approximately 7 kg. The average increase in body protein is about 3.5 grams per day during the first 4 months of life and 3.1 grams per day during the subsequent 8 months. By 4 years of age, body protein content reaches the adult value of 18 to 19% of body weight. As the growth rate drops rapidly after the first year of life, the maintenance requirement represents a gradual increase proportion of the total protein requirement. For the first initial month of life, requirements are based on the intake data because of the difficulty in accurately estimating allowances for growth and maturation of body composition. Infants breastfed by healthy, well-nourished mothers or fed human milk by bottle can grow at a satisfactory rate for about 4 months. Protein intakes by breastfed infants range from 2.4 grams per kg per day in the first month to 1.5 grams per kg per day in the fourth month, averaging 2.04 grams per kg per day in the first 3 months and 1.73 grams per kg per day in the next 3 months, as by WHO 1985 statistics. Breastfed infants in the United States grow satisfactorily by a mean protein intake of 1.6 gram per kg per day during the first 3 months. Probability assessment suggests that the true requirements appears to be less than mean intake. The figure proposed is 1.1 grams per kg with deviations of 0.1 to 0.2 grams per kg. The subcommittee has, however, accepted an average intake of 1.6 gram per kg per day as the requirement between the birth and the 3 months of age, the reference being human milk protein. The protein needs of an infant up to 4 months of age will be met if the energy needs are met contains protein of a quality and quantity equivalent that of human milk. The modified factorial procedure for calculating the protein needs of infants and children were examined by WHO group. Values were assigned for a maintenance requirement and an increment representing growth, the theoretical value for which was increased by 50% to allow for marked unevenness of daily growth rate and the inability of infants and children to store more amino acid against intermittent needs. Efficiencies of utilization was accepted to be 70%. These estimates were compared with data from the few studies of nitrogen balance in the age group of 6 months to 9 years. Neither the factorial nor the balance study estimates were consistently higher or lower across the age group. Because there are large gaps in the experimental data, the modified factorial approach was used by the WHO group to estimate needs for all children. The international values are accepted by this subcommittee in establishing average requirements for reference protein beyond the age 3 months. The coefficient of variations in the requirements calculated in this manner is assumed to be 12.5%, the same as the established for the maintenance requirements in the adult. The factorial determined average requirement is accordingly increased by 25% to derive the recommended allowances for reference. Students, let us sum up our talk. Most longer studies should provide a better basis for determining protein requirements, that is, they would permit the measurement of variables such as alteration in lean body mass or in growth rate of children which respond more slowly to dietary inadequacy. In few long-term studies that have been reported, investigators have explored the usefulness of various biochemical indices, but no agreement on a sensitive and reliable marker have been reached, because the human body can adapt to low and high intakes of nitrogen, and there is a substantial difference between intakes barely sufficient to compensate or loss to permit growth and intakes that may be associated with harmful effects. Since there are few criteria by which to evaluate the significance of the rate of protein turnover and pool size, value adjustments must be made so as to what is desirable in adults. For children, protein required for growth is relatively small compared to the needed for the maintenance. Nevertheless, satisfactory growth is a sensitive indicator of protein and nutritional status. The requirement for protein is reasonably well established for the very young child and the young male adult. For other age groups, much less information is available, and protein needs are estimated in parts by interpolations and extrapolation based on reasonable biological principles.